Now what's going to happen here, we need to design this footing. We need to find out the amount of reinforcement that you have at the bottom. Finding out the amount of reinforcement when it comes to foundation is going to be following this slide set number 3, the very first one that we started with, when you have a rectangular section, and this rectangular section exposed to a positive moment, if you like. So positive moment means that you have a tension at the bottom. This is where you need to put the reinforcing bars. And there is no top reinforcement, and the section is going to be a rectangular section. So this section here is not a T section. It's going to be very simple, and this is the way that you find out Feynman. And of course, you have this load combinations that we went through before. This is going to be for the LRFD design or reference design. And also we have the phi factor chart that you need to use. So don't forget, whenever it comes to any problem that have, if this problem here has like a moment demand, and you're trying to find out the strength of the section based on some given reinforcement, you really need to find out the phi factor. Even if some of my examples do not show that you're going to be doing the phi factor for it, you don't really need, that in my examples here, I'm not showing how to find out the phi factor, but if you're doing an exam problem, homework problem, or project, you need to find out the phi factor on your own. So we discussed this issue about the weight of the footing, whether it needs to be considered or not. So what I was saying, even if you just have a vertical load and you have uniform pressure right below the footing, so just forget about this pressure distribution. Let me just assume that you have uniform load coming like this, right? Like coming upward. So the stress here is going upward like this. So if this is stress here, when you were developing it, when you were finding out the amount of stress here, if you have included the weight of the footing in there, it means this stress here includes the weight of the footing as the big total load coming from the top. Can give you here quick numerical example. You can say if this load equals, just throwing there a number, right? Not related to this problem, all right? If I put here, let's say 500 kips, and this footing weighs about, I'm gonna say maybe, let's say 10 kips, just for school discussion, or let's say 4 kips, just 4 kips. Now, you have 2 ways of solving this problem. One way to do it is to disregard the weight of the footing, this 4 kips, take the 500 kips, divide by the contact area between the footing and the soil. And with that, you're gonna get here Q. You're gonna say this Q equals, we're gonna call it here Q net, is gonna be equal to 500 divided by A. So in this case, I just ignore the weight of the footing in my analysis. I can include the weight of the footing in my analysis if I wanted to. And in this case, I'm going to say here Q, and there's going to be gross, equals 504. 504 divided by A. Now I guess the gross bearing pressure is going to be larger than this Q net. Now I need to design my footing for the reinforcing, not for finding out the contact area. Now, you have 2 ways of doing it. You can consider the Q net or the Q gross. It's going to be up to you.
Professor, is the Q net 500 over A or 50 over A?
Why 50?
Because you put 50.
Oh, the one at the bottom here? No,
Yeah.
I seen that I didn't press enough.
Oh,
Yeah, thank you for bringing this to my attention. I'm going to say 500 divided by 8. Thank you very much. Thank you. So I have 2 ways of doing it, as I was saying. I can consider the gross bearing pressure or the net bearing pressure. This is going to be up to me in this case. So if I used here Q net in my analysis, it means the footing weight was ignored. And in this case, I can just take this pressure, multiply by the width of the footing, multiply by the cantilever length, twice, divide by 2. With that, I have the moment. But if I want to find out the moment based on this gross pressure, I need to subtract the weight of the footing, because the weight of the footing is going to be acting against this pressure coming upwards. And in this case, I'm going to end up with exactly the same moment value, right? If I have used the 500 kips only and find out the net pressure. Meaning, whether you use the gross or use the net pressure, you're going to end up with exactly the same moment on the concrete section of the footing. Are you good about this? Is everybody clear about it? Yes?
Yeah.
Yeah.
Okay.
Yes, sir.
Okay, great, good. Now let's continue here with our example. Now I can take these numbers out. I don't want them to stay. Otherwise, someone's going to say, what is this 4 kips come from? Or what's that about? So I can just take this out. Now, in this case, when I have moment and axial load, like vertical load on the footing, I end up with pressure on this side was equal to 8 ksf. This is coming from adding the pressure from axial load and the pressure from moment to each other. And this one was subtracting Fp minus Fm, end up with 2 ksf. Now, this pressure that I used here, as it was given the problem, it says that this force here is service. Now I need to put it as an ultimate. So if you need to do the size of the footing, you do it service. If you need to do the moment or punching shear or one-way shear, you need to use the ultimate. Now, how can I get to ultimate level? Start from the surface level, multiply it here by a factor of 1.4. So, okay. Now I have the stress, and one side is going to be 11.2, and the other side is going to be 2.8. This is going to be my critical section for moment. It's going to be right at the face of the column. And this trapezoidal here, it is kind of tough to find out just one force for this trapezoidal force. My problem is going to be the location. Where is going to be located at? So if I say, for example, someone's going to say, why don't you just consider this force coming upward to be just one force instead of having two forces? And the way that you find out this force, you see here 11.2, which means the total coordinate from here to there. And then you add 7.7, which is the stress right at the face of the column. Divide by 2, multiply by this width, multiply by the total width of the footing. I'm going to say, this is nice. I don't see a problem with this. My problem is going to be the distance from here to there. How much is this? You cannot figure out the location of this reaction. So you cannot really find out the moment for it. An easier way is to divide this into two forces. I'm going to have one force here for this rectangular stress distribution, and the other one is going to be F2 for the triangular stress distribution. For the first one, it's going to be located at x1, and x1 here, it's going to be simple. It's going to be x over 2. It's going to be 1/2, because you have here rectangular distribution. In the triangular distribution, this x2 is going to be 2/3 of this x. Why? Because the centroid of this triangle shape is going to be at 1/3 of the height of this triangle. 1/3 of this is going to be 1/3 of x, and the remainder is going to be 2/3 of x from the face of the column. Also, I've been asked about this value here. Where is the 7.7 coming from? Because in my analysis, I did 11.2 and 2.8. All of a sudden, I'm throwing there 7.7. You should be able to do this by interpolation. If you know the slope of this line, now how do you find out the slope? You can say 11.2 minus 2.8, right? This is going to be the difference between the two. And then you divide this by the length of the footing. Here's the length of the footing that was given to you, 12 feet. So once you find out the difference between the two values, divide out by this distance, and then multiply it again by x. So you take the slope, multiply by x, it's going to give you the amount of drop from 11.2 to 7.7. Does this make sense? You guys know how to do interpolation. It shouldn't be a problem, I guess. So now we know where's the 7.7 coming from. Now the moment at this face is going to be equal to F1 times X1. You take this F1 times X1. So what you do here, you cut the section right at face of column, and then you start to take the moment. You say F1 times X1 plus F2 times X2. With that, you have the total moment at the face of the column. So I guess I'm doing here the same concept I have used when I have a footing and I have only vertical load. The difference is, instead of having uniform distribution of stress, I'm going to have this trapezoidal distribution of stresses. And for that, I'm going to have here two forces. So what I'm doing here, I'm going through this slide set number 14. At the same time, I'm kind of doing also a review for your midterm. Because in your midterm, you're going to have a footing, but you're not going to see moment on it. You're going to see only axial load, vertical load on it. All right. So I'm taking the same section again, same elevation. I have two forces. I was able to find out here the distance x, and this distance x is going to be equal to the total length, 12 feet. You subtract the column, divide by 2. You have here 5 feet. And then F3 ultimate, which is a 7.7. I'm showing here how do you do, I'm going to see here, finding out 7.7. This is going to be based on interpolation. You start from 2.8 and then you add to it. So the 7 feet is going to be from here to there. This is actually 7 feet. Because one cantilever is going to be 5 feet and the column width is going to be 2 feet. You have total here of 7 feet. So this is here is going to be 7 feet, right? 7 feet, which is the 7 feet here. You see, it's giving my 7 feet that I'm talking about. 11.2 minus 2.8 is going to be the drop between the two values, 11.2 to 2.8. You divide this by 12, which is the length of the footing to get you the slope. And then with that, you end up with 7.7. Now you have the two forces. You should be able to find out the two forces. And don't forget to consider the width of the footing to be 10 feet, which is this 10 feet that you see here in the analysis, right? It be 10 feet the width of the footing, normal to the screen. Same thing here. Now you have two forces, and certainly x1 is going to be equal to 2.5 feet because this x is equals to 5 feet. So we can say this here equals to 5 feet. So x1 is going to be equal to 2.5, and x2 is going to be 2/3 of 5. With that, I have the moment. Now, what do you do once you have the moment? Right after you have the rebar location, and then you run through this that we have done before. Do you guys remember doing anything like this before? You try to come up with an estimate of the reinforcement. You set phi min is going to be equal to m sub u, as you see here. And then you assume that d minus a over 2 is going to be equal to 0.9 d. And with that, you find out the amount of reinforcement needed that you need to resist the flexure for the moment. And then you try a certain number of bars with some bar diameter. In your midterm, I'm going to specify the rebar size that I want you to use. So you can try. You can say, for example, here's this many square inches of reinforcing that I need. So I'm going to try, let's say that you're trying number 9. So you can say I can go with 12 number 9. Why? Because number 9, it has a cross-section area of 1 square inch. So 12 number 9 will cover this amount of reinforcement that you have in there. After this, you need to refine your work, find out the A value. And then after you do the A, what is missing here? And then find out A, correct, and phi factor, which is this phi, like the phi symbol. So you need to do this on your own. So you can find out A, and then you can do C, and then you can do C over D, or you can do the strain and the strain. And then eventually, you're going to be able to find out the phi factor. Once you do this, also you can find out phi min. Now compare it with m sub u, which is great. And you see this, it says here you need to determine the C over D ratio and confirm that the phi is equal to 0.9. How about the other direction? I guess the other direction, that's going to be a different story. Why? Because when I cut the section this way, I know that the moment is going to be acting only in this direction. So moment is going to be causing moment, right? Is going to be coming like this. Moment is not coming the other direction, meaning that the stress distribution here below the footing is going to be like this. So if you like to cut a section in the other direction, let me go here to the plan. So the section that we cut it right here. And that happened to find out the reinforcing in this direction. This gave you the reinforcing, right? And we say maybe it's going to be 15 number 8, right? We put it in this direction. So we're going to call this I'm gonna call this section here, I'm gonna call it section 1. So when you do section 1 here, you find this AS1. Someone's gonna say, how about the reinforcing in the other direction? I'm gonna say, like what? Someone's gonna say, how about this reinforcing here? How much would you put here? You say, in this case, you need to take section 2. And your section 2 is gonna be right here at face of the column in here. So I'm gonna call this to be section 2 to find out AS2. So this here is gonna be AS2. Now the stress distribution is not gonna be trapezoidal in this side. It's gonna be weird looking, right? It's gonna be completely different because the pressure here, as we have seen, it is like this. So when you cut a section right here, which is gonna be parallel to this surface, stress distribution is gonna be completely different, and this is gonna be a different story that we need to cover later on. So I'm gonna stop at this point here, and then I'm gonna be switching to working on review for your midterm. Any questions on this section that we just covered? Yes?
So just to be 100% sure I'm understanding this, you mentioned that you will give us the rebar, correct?
I will what? Specify the rebar? I'll give you the rebar sign. Right?
Okay, thank you.
Yeah. Otherwise, anyone can just use number 7. Another person is going to be using number 8, number 9, number 10, because there's no guidelines. And in this case, I need to solve maybe 7 or 8 problems to be able to grade your exam, which is going to be wasting for everybody's time. Any other questions on the moment issue and the section location and this kind of things? Ready for the midterm review?
Yes.
Yes? All right. Right now it's 4:22. I'll see you at 4:25. So stay around. It's giving you 3 minutes. Is everybody back?
Yes.
Yes.
Yes, all right,
Yes.
great, very good, very good. So I don't think I need this. Now I'm gonna go back here to the first slide set. Slide set number 3. In this slide set here, this is gonna be for rectangular section, exposed to positive moment or maybe negative moment, and you don't have any compression reinforcement, and it is not a T section. You guys have any questions on the use of this beta 1 for different concrete strength and finding out the A, right, for compression block depth? I guess lots of people scored very well in your first midterm about this problem. And this is exactly what you're going to see in the foundation design problem. Then after that, you find out MN, and of course you do this phi factor. And if you remember also that you have a few load combinations. So the two main combinations that we use here for gravity analysis going to be these two load combinations. I just want to be sure that you guys are aware of them and you know about them and nothing is new about this. You guys remember these two load combinations, right? It's going to be 1.4 dead versus 1.2 dead plus 1.6 live load. We covered this already. This is kind of the first slide that I want you to be aware of and I want you to use because you're going to see it in your midterm, right? Okay. Any questions on this? Okay, no questions, it seems. You're going to see a problem in column design. All right, thank you. Column design is going to be there. I need to give you a column. This is one of the new things that we considered after the first midterm. This column here we call tight column, and it's going to be the spiral column. And generally speaking, you'd like to have phi pn is going to be greater or equal to p sub u. This one here, this is what we call demand or ultimate. So let me put it here. Here are all the names that you may consider. You're going to see here demand, which is the same as ultimate. Same as factored. Right? This is all the same, which is all of this. You can call it demand, ultimate, or factored. How about this one here? I have also a few names for it. You can call it capacity. How about the word design? Where's the design? Design, is it the design or this is going to be the design? You can say also the design. Any other words beside the capacity that I can use here? You can call the strength. So what's the capacity or strength? It's going to be how much the column can take. It's like a limit. It is not based on the applied load on the column. But this one here, this is what we call demand. Also, we call it ultimate, we call it factor, we call it design axial load, right? All of these names are okay. And this means the amount of load that you are planning to put on the column. You want the column to support. So you need this to be greater than this. If this value here is going to be greater than this value here, it means your column is unsafe code-wise. Okay. So I'm going to have a tight column and a spiral column. And both of them, you're going to see it in the exam. So the first one here, the first slide set is going to be for tight columns. You see, for tight columns, we use this curve. We use this line, right? And also use this line for the phi factor. This for columns. If you have axial loaded column and no eccentricity, you're going to have a phi factor of 0.65. So you don't really need to do interpolation, or you don't need to think about tension control. It's going to be compression control. So if you just have an axial load, it's going to be all compression controlled, and this is going to be your phi factor. We have this simple equation, and this simple equation here, it is for axial loaded column with no moment, but it allows a little bit of moment. And this moment, right, is going to be called the small eccentricity moment. This is why we have this 0.8 factor. We have gone through this example before, or this equation. We know that this is going to be the cross-section area of the vertical steel, yield strength, cross-section area of the column, and vertical steel on the column. What's the column minimum reinforcement ratio? I'm going to say here 1%, maximum 8%. So for any column, if I'm going to go back here, you need to have at least 1 rebar at each corner. So in this case, I can have 4 rebars. I also can have 6 rebars. If I put 1 rebar here and 1 rebar here, I can have 6 rebars or 8 rebars or 10 rebars or 12. I cannot have 11 rebars because you need here to see some symmetry in the column. Meaning if I'm going to be drawing here a vertical line and here also I'm going to have a horizontal line like this, I need to see here symmetry between these 4 quadrangles if you like. So when you choose the number of rebars, don't go to 7 rebars or 9 rebars. It needs to be an even number. Spacing between ties is giving the example. So you need to study this. And we have good examples. We have lots of recorded videos on this. So you shouldn't have a problem. And don't forget, if the column is given California, your maximum is giving 6 inches. Okay. So you can see that. Very good example that we have in here. The spacing. The clear distance between ties. You remember this clear distance between ties? And then we said that we should be able also to put like an even number, and you see you can have lots of rebars added in a certain way. Same thing, PPN for axial loaded column, small eccentricity. Any questions on this column slide set? Gonna go here to slide set number 10. So when we have the spiral column, difference in the equation is clear, and also we have a discussion here on confinement. So I'm gonna have a question on confinement. What do you think confinement is doing to your column? I'd like to hear from you guys.
It's just adding resistance, right, to one of the members.
Mateo, is Mateo there?
Yeah.
Yeah, tell me, what's the confinement doing?
It provides specific location.
You
It's
can read it. You have it right there. You can just
Okay.
read it.
concrete confinement is provided at specific locations of the seismic force resisting member.
Yeah, but we're not here talking about seismic, right?
Yeah.
So generally speaking, why do we need to have confinement in our rebars, in our columns? What does
Is
it
that for a
do?
moment?
What does it do? What the confinement is going to do to your concrete?
It enhances the concrete properties, including
Thank you.
strength.
Thank you very much. It's so simple. You can just read it. All what I ask you here to do, just look at this, try to remember what was that about, right? It's going to provide, it's going to enhance the concrete properties. Like what? Now I'm making it tough, right, Mateo? So what should I do here? If someone's going to be asking me this question, I'm going to say, let me look, what else do I have in this slide? I'm going to say, I have this curve. What is this curve about? You see the way I'm thinking here? First, I can read this for quick. Second, look at the properties. What is this property called? Do you know? On the y-axis. Strength?
Yeah.
Strength? How about in the x-axis? What is the name of this? What is this called?
Concrete strain.
Strain. Where is the confinement versus unconfined? Unconfined means like with no confinement, right? This gives you the performance curve, right?
Yeah.
What does mean performance? Performance means you apply some load and this gives you the amount of strain. This is what you're going to see out of it. So we call this the performance. And here's going to be the confined concrete. Now, can you compare this to that? Do I need to compare it for you or can you figure it out yourself? What is the difference between these two? You tell me what happened when you provide the confinement.
When you provide confinement, you get more concrete strength.
Yes, absolutely. And what else?
And your concrete strain becomes larger as well.
Is this the amount of concrete strain that I'm going to have in the structural member when I apply the same load? So this load is going to be here the same as this load, or the load is going to be different?
Wait, can you repeat the question?
Okay, because some people would think and say, does it mean for the same column, I'm going to put the same load, and then all of a sudden confined concrete, I'm going to have higher strains than what I would have in unconfined concrete
Yeah, yeah, you'll get higher strength in
for the same column load?
um
No, it's
no.
not the same column load. So what is this? I mean, why the strain here is higher than the strain here? I'm gonna say this gonna be the attainable strains, which means the strain limit. This column here is gonna be able to take lots of strains without failure. But this one is gonna be failing much faster. And here's the difference between the two. So this is gonna be performance curve. It is not because you apply this much load and this is what you get. For example, if you apply here the same load, what's gonna happen? If you apply the same load, you're gonna have the same stress in the column. Here we're not talking about how much the column is gonna be able to take as a stress. Look at this. This one, this chart here is for how much the column is gonna perform. How it's gonna perform, you just look at this. But how much stress would you do with the column under some given load? It's gonna be the same stress, right? So you have here two structure members next to each other. One of them is gonna be confined, which means higher quality. The other one is gonna be lower quality, concrete. And you can think about this if you have two different materials, right? Let's say one of them is made out of aluminum, the other one is gonna be steel. And then you start to load both of them. You put here a pound, you put here a pound. And the cross-section area of them is gonna be the same. Now, how much is the stress that you're gonna have in each one of the spacements? You're gonna say it's gonna be the same because you take this 1 pound divided by the cross-section area of this spacement or sample, it's gonna give you the same stress. So actually the stress within the sample itself or the column is gonna be exactly the same. This is the stress that you develop from putting this load. But if you ask me a question, which one do you think is gonna be resisting more force? Yes, of course, it's gonna be the steel. You can load the steel with much higher, it's gonna be there. But if you put in the aluminum, it's gonna be coming down a little bit. This makes sense? So this chart here, or this curve, is gonna be for the performance. It is not for how much load you put on it, right? This is gonna be the capacity of it. So I guess we need to have a discussion on this. It needs to be in the exam, like one of these multiple question problems. I need to talk about the column confinement. Also, I need to compare between tight column and the spiral column. What is the difference between the two? Which one do you think is gonna be stronger and how much ratio? Do you guys remember the ratio between spiral column and tight column?
It was the spiral that was stronger, but by
How much?
0.85 or 0.8, I think.
Yeah.
22%.
How much?
22% increase.
Yeah,
in
22%, 23%.
Oh.
Absolutely. Yeah, usually we say about 20%. If we want to just run quick numbers, we just take whatever that you have for the tight column and jack it up by 20%. All right. So I guess you guys remember this equation. What is that for? This is going to be for the amount of spiral reinforcement that you need to put in there, right? So be sure that you study this equation. If this equation is needed, I'm going to put in the cheat sheet. In the formula sheet, it's going to be there. Whatever equations that you need, I'm going to put it there.
Are you gonna upload an equation sheet like last exam?
Absolutely.
Okay, thank you.
No problem. Here's one example. This is going to be a very good example. It is detailed. It shows you how to find out VPN, right? And then it shows you how to find out the tie reinforcement or the spiral reinforcement and check it, right? With all the checks needed. Okay. You go here to the third slide set for columns. It's going to be axial loaded column with some eccentricity. And then it says here, this is a very good example that you need to study 9-5. You have the column with small eccentricity, which means just VPN. Excuse me. Like in this equation. And then you have another one with eccentricity of 5 inches. And then the third one is give balanced strain condition. I see this one here, balanced strain. What's the balanced strain condition? Anyone recall? Do you remember, Mateo, or no?
No, I don't.
Okay. The balanced point, just to remind you here, is going to be this point. At this point, the concrete is reaching a strain of 0.03, and the yield in tension is going to be reaching the yield point, 0.002. in the same time. Do you have a good example for it? I'm gonna say yes, it's right here. It starts from page 13 of the slide set 11. So for this balanced condition, at the end of the day, you need to find out the moment component, which means this value here. You take vertical distance, and the axial load component. These two values here. Very good example. I want you to study it and be sure that you're ready for this. You don't want to lose points in your exam because you didn't prepare for it. So I'm telling you, it's gonna be there. How about if I give you a chart like this? I'm gonna ask you here a simple question. Would this column be able to take, let's say, a load combination of an axial load of 1200 kips and 500 kip foot? So I was gonna say, repeat this again. Yeah, I'm gonna say, okay, here's the values. 1200 kips and 500 kip foot. Yes or no?
No.
No.
Oh,
No, this one wouldn't.
How's that? Can someone explain, please?
It's outside of the curve, the blue.
This is 1200, it's gonna be here. Oh, it's gonna be outside of this. Okay, but it should be able to take 1200 kips and maybe 400 kip foot. Am I correct?
Yes, you're
Yeah.
correct.
Okay. Can someone help me with this point here, the definition of this point? What is that point about?
It's tension control there.
Yeah, tension control meaning what?
The concrete crack.
Isn't it the self-weight of the concrete?
Now, is the concrete here in tension or compression?
Tension.
In tension?
Yes.
I thought this was in compression last time.
I mean, is the compression here is gonna be in the top and it's gonna be in tension?
Is it compression because it's negative?
No, this is tension side. Only for column design. Only for column design and for this specific chart. So I'm gonna say this is gonna be compression side and this is gonna be the tension side. I said, okay, great. So now I understand. How would you find out this tensile strength of the column? You see the name that I use here? I mean, if you are not present now, if you are not giving me enough attention, you're gonna lose it because you're gonna be asking me this question. What's the tensile strength of the column? Where is that point? I'm gonna say it's gonna be this point. It is this value here. Do we have an equation for it? I'm gonna say, here's the equation. Have you seen it before? Yes. You have it recorded. And I'd assume that you're gonna be watching this recording before your exam. And you're gonna be thinking here with me. You're gonna say, well, it is not really based on the concrete because concrete is gonna be cracked. So it's gonna be equal to phi factor. How much is the phi factor here? Someone's asking. Says, how much is this phi factor here? Can you guys help?
0.9.
0.9. Why? Because it is really in tension. So the other one was in flexure. When the strain went beyond certain limit, we said, well, this gonna be like tension control. This is real tension. This is actual tension, the pure tension control, right? You can say times AS. Is this AS of the ties or AS of the vertical rebars in the column?
Main bars.
Of the main bar, the vertical rebars, and Fy is gonna be the strength, like F sub Y for the steel 60K sign, and most sustain. So I say, okay. So you guys, you understand this point, and you know this point. You remember what we call this? Anyone recall the name of this point? Yes.
The balance point.
So I need from you to figure out, let's say for this given, yes, say this value here is gonna be the amount of moment that the column is gonna be able to support, and also here the amount of axial load for the same point. You need to be able to solve for this. Very good. All right, great. Now let's work here in foundation design, right? Because you're gonna see here a column, couple of column problems, and a foundation design. Here's foundation design. Number one, what is this about? I'm gonna say, you guys remember the tributary area that you have used in your project? You understand it well? I'd assume so, right?
Yes.
Okay.
Yes.
So for this tributary area, if I give you here dead load and live load and say that you have 7-story building or 6-story building and plus a roof, and they give you an elevation, you can count number of floors, right? Multiply by tributary area, multiply by dead load and live load, and also the roof. You need to consider the roof, combine it, and of course use a 1.4 dead versus 1.2 dead plus 1.6 live, correct? So okay. You remember this problem here, example 1, right? For the reinforcing. How do you do here the reinforcing? Now, in this case, we were discussing here, why would you take the cover to be that much, right? And how about the depth? In your midterm, I'm gonna give you the depth. I'm gonna say, use this depth in your analysis, and that's it. So you're not confused, right? So I don't want two people, each one of them to come up with different depth. Now I need to chase it. So I'm gonna make it simple. I'm gonna give you here the depth for the footing. Any questions on this? When you do the critical section for moment, critical section for one-way shear, and also the punching shear. This is gonna be also critical. This is gonna be the one-way shear, right? It's gonna be at D distance from face of support, one-way shear, and then finally you need to see this punching shear problem, which is this problem here. This example. So example 3 is gonna be there in your exam, right? And this example also 1 and 2. So this slide set is gonna be very important. Slide set number 12. Now, do you think I need to give you this equations in the formula sheet?
Yes, please.
Yes, absolutely. I'm not expecting that you'd memorize this. Are you guys good? Any
Yes.
questions in your midterm?
Excuse me. Regarding the tributary area,
Yes.
what about, do we have to include, the dead load and live load that you gave us actually is going to be included the beam weight that contributed
Yes.
to.
Yeah.
So we don't need to.
I'm gonna state it. If I want you to calculate it, I'm gonna say calculate it. If I say this includes weight of concrete members, it means you don't really need to double count it, right? You don't calculate it, correct?
Yes.
Okay,
So
great.
just
All right. Yes.
and just for clarification, how does it work? I mean, I know that we have to, the actually beam load is going to be through the tributary through the length of the beam goes to the column. So just we have to see if, for example, if we have 10 feet of, assume that we have only one kind of beam in that tributary area, which is that the length is 20 feet in total. So that's going to be only that 20 feet that's going to contribute in that section.
This is your tributary area for this floor plan. How much is this? You say A equals tributary area, right? You're gonna say this here 26 feet, 26, and this gonna be 28, but I'm gonna say 26 by 28. Isn't this good enough?
Yes, it's
This is
780.
tributary area. That's it. Now we are done with the tributary area.
I know,
For
but
this, yes.
I'm just talking about the load.
Yes. Now the load is gonna be given to you. I'm gonna say here's the load, dead load. I'm gonna say equals 160, right? PSF. Life load equals, I'm gonna say, let's say 60 PSF. So what do you do next? For one level only, you're gonna say, here is the load for one level only. P dead load. You know what's P dead load? X load comes from dead load. It's gonna be equal to, how much is 26 by 28? Let me try this. 728 times 0.016.
But actually that dead load actually included the weight of the beam also.
Yeah, it's gonna state in the problem if the concrete member or the weight of the concrete member is included or not.
So
if I want you to include it, assuming that is already included, then you're done with the dead
I know,
load.
but assume that is not included. So how are you going to be solve that situation.
Okay, so let me here take this problem. I'm gonna say that was just a discussion on this column. I'm gonna go here to another column, right? I'm gonna say, let's take this column here. How much is the tributary for this one?
Same
From it.
thing. Same thing.
Let's say same thing. I'm gonna say here dead load and live load. I'm gonna put them here, but I'm gonna say here dead load is, I'm gonna put it here 10 PSF and live load is equal to 6 PSF. I'm gonna put here weight of concrete is not included. Concrete slab is not included.
Slab and beam also.
There's no beams. Okay, in this example that I give you here, I don't have any beams, all right?
No, I just consider that there is some beams.
I don't want to consider beams here in this example. I'm gonna say concrete members, how about that? Because someone's gonna say about the column weight, right?
Yeah, column, I'm just.
Is it good?
Okay, let's see.
Does it cover? Okay, good, all right. So let's say concrete weight is not included. So what is the information about concrete provided to you? So I'm gonna say, here's the information provided about the concrete. Yes, say for the concrete, you have 12-inch thick slab. That's it, no beams. I don't have beams. I decided not to have any beams. Otherwise, you want me here to solve for the beam weight right now, correct? I don't want to spend my time doing this. I want to get to the point. What's the point here? I'm gonna say, finally, dead load equals, it's gonna be equal to this 10 PSF plus, can I have here 12-inch thick concrete? So I'm gonna say 12 divided by 12 is gonna be 1 foot thick, multiplied by 150, right? What's 150? PCF, unit weight of concrete, right?
Yes.
Equals, how much is that? 160 PSF. Always give me almost the same number like here. Yes, I understand. That's why I made the number this way, to make it simple for you. So it is going to be one of the two ways. Either I'm going to give you the whole thing inclusive. I'm going to say here, weight of concrete members. Weight of concrete members are or is included. All right. See this? So when you see here, weight of concrete members is included, what do you do? Do you need to find out the weight of the concrete?
No,
or
no,
no?
no. I
No,
understand
you're
that.
done. It is there, right? And in this case, I'm saying weight of concrete members is not included, which means you need to figure it out yourself and add it. So I'm not going to say here, determine the weight of the concrete, because I'm saying it is not included, and then finally find out the design load. What's the design load for you? Is it P sub U or PPN? What is the design load? Can someone help me with this?
It's going to be factored load there.
Like P sub U or PPN?
P sub U.
Thank you. All right, this is going to be the design load. So design load is the same as demand, same as factor load, right?
Yes.
Capacity and the strength is going to be the same thing, which is PPN.
So we don't have to multiply by 1.2 and the 1.4.
Multiply what? The dead load and live load?
Yeah.
Who said that? I didn't say that. I'm saying here, here's dead load and live load. I'm just putting here definition for the design load. This P sub U is going to be based on the load combinations. You need to have all of these load factors when it comes to here, right?
Yeah.
Does it make sense?
Yeah, it makes sense.
Okay, great. So again, you're gonna have a column design, short column, or let's say small eccentricity column, balanced point, tensile strength of the column, load combinations, P like M sub U and P sub U, given some combination, ask you about the capacity. Is this column okay or not? Also, you're gonna have a footing design, right? Footing design, I'll give you here the axle load, footing dimensions, the depth, the rebar size. I'm gonna say design the rebars. Also, you need to have one-way shear punch, right? Check. And also, you're gonna have also punching check in the column. And maybe a couple of simple problems here, like multiple choice, so that you can gain some points in an easy way.
Are you gonna have enough time to finish?
Yeah, you will. Eva,
Are we not doing a conceptual quiz like how we did it last midterm?
what is a yeah, it's gonna be conceptual quiz. This is correct. It's gonna be simple stuff. You can just read it and finish it in a couple of minutes. It's
Now
gonna be maybe
these,
two problems only 2 issues that I want to talk with you about conceptually, and I guess we discuss them today, right? Can
Mhm.
someone guess which ones? What were the 2 issues we discussed conceptually? I said what?
Concrete confinement.
What?
Confinement.
Concrete confinement.
And what else?
Balance condition?
No.
Was it the interaction diagram for the columns?
Did you talk about this? Confinement and tight column versus spiral column. Right? Did you discuss the difference between tight column and spiral column today? Did I mention it quick? I said that you need to know the difference between the two. Why one of them is stronger than the other? I say, yeah, because of confinement. I see. So these 2 questions kind of related to each other. And which one is stronger? The tight column or the spiral column? If you have the same
Spiral.
cross section, why? You're gonna say because of confinement. By how much?
20%.
By 20%.
What is the reason in the equation? Can you tell me how the code recognizes this? You're gonna say different p factor and different small eccentricity factor. Is this true? Or I just forgot the whole thing? Let me show you.
They have different B factors.
Yeah, here's the phi factor. Here is 0.65 and 0.8. How about on the other one? 0.75 and 0.85. Now I understand where the difference is going to be coming from. The small eccentricity effect and the phi factor is different between tight columns and spiral columns. All right, I guess I'm done. I told you what to expect in the exam. And I'd say dedicated students should gain like 100% in this exam after what I have told you here. Because you have the material and you have a very good idea on the problem here, and you can just solve this exam before you go there. You solve the same ideas. You make some problems, you solve them before you go, so at least you know that you can do well. If you didn't, and you're gonna be just waiting and say everything is gonna be okay, now I know where to find the information, well, you may not perform that well.
Professor, on the topic of foundation design, will the midterm cover up to slide set number 14? So I noticed that there's 3 slide sets on foundation.
Well, I told you exactly how the foundation problem is going to look like. Now I want to hear it from you. What did you hear from me about the foundation design problem?
You said that you would give us the depth for the footing, the critical section for shear, and the punching shear is what we might, or we're going to have to calculate in one
Okay.
other item.
Let me repeat it here for quick, so that no one's going to say, oh, I was not giving enough attention. I understand. Okay, you're going to have a problem like this. So you're going to have a footing, like one of these footings, right? One of these footings. I'm going to say, here's the footing, right? I'm going to give you the size of the footing, axle load. So what do you need to do? Find out the reinforcing. Do one-way shear check. Do punching check. Here's a punching check, like in this example. So this gave you slide set number 12. Did I say anything about number 13 and 14? Did you hear me saying anything about it? Did I open them today?
No.
Okay, great. So should you expect problems from these 2 slide sets, 13 and 14?
No.
Should I bring problems from 13 and 14 or no?
Please no.
Thank you.
No,
Okay,
thank
no,
you.
because I didn't bring them in. I mean, why would you expect something that I didn't? I'm just telling you how the exam is going to look like. Which essentially I just covered everything. I mean, I just talked about everything we covered so far. All right, if you like, if you still have any questions, please join the office hour in 5 minutes from now. Otherwise, please sign out and you have a good night.
Quick question. Do we have another submittal
You have a submittal on Wednesday, right?
on Wednesday? Okay. I just wanted because I couldn't see it on the canvas. I didn't know if you
Yeah.
uploaded or not.
I haven't seen it either.
Okay. All right, we'll see you tonight. I just need to show it. All right.
Excuse me, one other question, just follow up. Did you have a chance to look at the grading for homework number 5?
Are you telling me it's not posted yet? Number 5?
No, no,
Okay, yeah, because you told me it's out of 5 versus out 10
Out of-
versus 20. I see
Yeah.
what you're saying. No worries about it. Don't worry about it.
Thank you.
This can be done at any time.
Have a good time. Thank you.
Good night. Okay, bye.
Thank you, Professor.
Thank you.
Professor,